Today we're going to be talking about binary trees. What are binary trees? Binary trees are recursive data structures in which every node has a left child and a right child. You can also think of it like this. One node is a binary tree, and the left and right child of every node is another binary tree. Notice binary trees aren't linear data structures, as in they don't store data in a linear way. They aren't like linked lists in that regard. However, you can still represent a linked list-like object using a binary tree model if you have one where every node has one child except for the last child. So let's go over some terminology. The root of the binary tree is the first node in the tree, and this is usually the node that you pass into other functions. There's also the leaf node, and this node is a node that has no children. And then we have the edges that link between the nodes. It connects the nodes together. The height of a binary tree is defined as the longest path from the root to a leaf node. So to show that, I have an example here. So let's say you have this binary tree. Well, there are 4 possible leaf nodes that we can look at. There's 1, 4, 7, and 13. In order to find the height, we would just have to trace the path from either 4, 7, or 13. They all have the same depth. So let's just trace up from 13. We go up to 14, 10, and then 8. So we've gone up 3 nodes. So that means the height is 3. You could also write the height is 4. It depends on how your course wants to do it. As in whether you count a tree with one node as height of 0 or height of 1. Now I alluded to depth earlier. Depth refers to a single node. It's not for a tree. The height refers to a tree. So the depth of 3, for example, here is 1. And you can think of the height as simply the largest depth of all the possible nodes in the tree. So then you might be wondering, why do we use binary trees? What's the point? The short answer is for more efficient searching. Recall that in a linked list, to search for a certain node, the worst case scenario is big O of n. In other words, if your node happens to be at the end of the list, you'd have to search through all of the nodes in order to find what you're looking for. But there are various types of binary trees that let you search in a more efficient manner. Examples like the binary search tree, AVL trees, weight balancing trees, and red-black trees, as well as heaps. These trees all let you search in order log n time. Here's an example of a binary search tree where the left side of the tree is less than the root and the right side is greater than the root. This is just a brief example, so I'll go over binary search trees more in depth later. Let's see how we would search 7 in these 2 data structures. In a linked list, we have to start from the head, which is in this case 8, and we have to traverse through all the nodes. So we go from 8 to 3, then 3 to 10, then 10 to 1, etc., until we get to 7. And we had to go through 7 nodes to get what we were looking for. Now compare this with the binary search tree. In the search algorithm for a binary search tree, what we do is we start from the root of the tree and we check if the number we're searching for is less than or greater than the number at the root. So if it's less than, we would go to the left. In this case, 7 is less than 8, so we go to the left. And then we just continue on. 7 is greater than 3, so we go to the right, and 7 is greater than 6, so we go to the right, and we found 7. And it took only 3 steps. So you can see in this example how powerful binary trees can be. There are a lot of examples of binary trees, and I'll be going over them in future videos. In my next videos, I'm probably going to be going over some traversals like depth first search and breadth first search for binary trees.